So what happens when gravity just, well, wins? Completely and utterly.
Yeah, imagine a point where there's absolutely no return.
Like, not even for light itself.
Exactly.
Welcome back to the Deep Dive. This is part 4 of our journey through a brief history of time.
And today we're diving into chapters 6 and 7.
Which means we're talking about the big one, black holes, and also this really strange idea that maybe they're not entirely black after all.
That's the plan. Our mission, same as always, is to really get into these, well, frankly, mind-bending concepts.
It should be clear. Right. Detailed, yes, but understandable. We're looking for those aha moments.
Absolutely. Avoiding the super dense jargon, aiming for the core ideas.
Okay, so we've got quite a journey. We'll look at how these things actually form, what that point of no return really means.
The event horizon.
Right. And then tackle this seemingly impossible idea, Hawking radiation. The notion that black holes can, evaporate?
It sounds crazy, but yeah, that's where we're headed.
All right, let's jump in. Chapter 6, black holes. Where do we start?
Well, the basic idea is a black hole is a region in space-time where gravity is just overwhelmingly powerful.
So strong that nothing escapes. Not even light.
Nothing. Light, matter, information, it all gets trapped.
And this isn't exactly a new thought, is it? I remember reading about John Michell way back when.
That's right. 1783, he was thinking about stars that could be so massive and so compressed.
Compact, yeah.
Compact, exactly. That their escape velocity, the speed needed to get away, would actually be faster than the speed of light.
So even back then, the basic concept was there. Incredible.
It really is. And to understand how they actually form, we need to think about how stars live and die.
The stellar life cycle.
Right. Stars are born from these huge clouds of gas, mostly hydrogen, collapsing under their own gravity.
Gravity pulls it all together.
And as it collapses, the core heats up incredibly. Eventually gets hot enough to start nuclear fusion.
Hydrogen smashes into helium, releasing tons of energy.
Exactly. And that outward blast of energy pushes against gravity. It creates a balance.
That's our stable star shining away.
For millions or billions of years.
Mm-hmm.
But that fuel doesn't last forever.
Right. What happens when the tank runs dry?
When the nuclear fuel is used up, that outward pressure stops. Gravity takes over again, and the star starts to collapse.
And what happens next depends on how big the star was to begin with.
Precisely. It all comes down to mass. For stars, let's say less than about 1.4 times the mass of our sun.
That's the Chandrasekhar limit, right?
That's the one. Named after Subrahmanyan Chandrasekhar. For stars below that limit, there's this quantum mechanical effect called the exclusion principle.
The idea that particles like electrons really don't like being squeezed into the same state.
You got it. It creates a kind of outward pressure that can actually stop the collapse.
So the star settles down into something like a white dwarf? Or maybe a neutron star?
Exactly. Those are the remnants for the less massive stars. It's sort of, well, stable retirement.
Okay, but what about the really massive stars, the heavyweights?
Well, for stars much more massive than that Chandrasekhar limit, gravity is just too strong. It crushes everything. Even the exclusion principle can't hold it back.
So the collapse just keeps going.
It keeps going.
Relentlessly.
And that's when you get a black hole. The star collapses past a certain critical point, a critical radius.
And that boundary, that's the event horizon, the point of no return we mentioned.
That's it, the event horizon. It's not a physical surface you could touch, but it's the boundary in space-time. Cross that line.
And there's no coming back. Ever.
No way out. Think of it like swimming against a current that's faster than you can possibly swim. You're just pulled in.
A one-way membrane. Stuff falls in, absolutely nothing gets out. It reminds me of that Dante quote.
All hope abandoned, ye who enter here.
Yeah. Pretty chillingly accurate, isn't it?
It really captures the essence of it. And once you're past the event horizon, you're inevitably pulled towards the center.
Towards the singularity.
The singularity, a point of, well, theoretically infinite density and infinite space-time curvature.
Where our understanding of physics just stops working.
Pretty much. The laws, as we know them, break down there. It's like an endpoint for time itself for anything that falls in.
Infinite density. It's hard to even wrap your head around. And the book mentions something called the cosmic censorship hypothesis, keeping these singularities hidden.
Yes.
Yeah.
Roger Penrose's idea. It basically suggests that singularities formed by collapsing stars are always clothed, always hidden inside an event horizon.
So we don't see these points where physics breaks down directly. The universe keeps them under wraps.
That's the hypothesis. No naked singularities allowed, essentially.
Interesting. So despite this crazy singularity inside, from the outside, a simple black hole sounds. Well, simple. I think Werner Israel's work showed that.
It's quite remarkable, actually. Israel showed that a non-rotating black hole is incredibly simple. It's perfectly spherical,
And defined just by its mass.
just by its mass. If you know the mass of a non-spinning black hole, you know everything about its external gravitational field. That's described by the Schwarzschild solution to Einstein's equations.
Okay, so we have the theory. Inescapable gravity, an event horizon, a singularity. But these things are black, invisible. How do we actually know they're out there?
Great question. We can't see them directly, so we look for their gravitational effects on things we can see.
Like stars orbiting. Nothing.
Exactly. We find binary star systems where a visible star is whipping around an unseen companion.
And if that unseen companion is way too massive to be a regular star, or a neutron star, or a white dwarf.
Then a black hole becomes the prime suspect. A famous example is Cygnus X1.
And doesn't Cygnus X1 also blast out X-rays?
It does. That's another key piece of evidence. The idea is that the black hole's immense gravity pulls gas off its companion star.
Look, a giant cosmic vacuum cleaner.
And as that gas spirals inwards faster and faster, it forms an accretion disk. Friction within this disk heats the gas to millions of degrees.
Hot enough to emit X-rays, so the black hole reveals itself by how it eats, basically. The X-rays are the crumbs.
That's a good way to put it. That intense X-ray emission is a strong signature. Another line of evidence comes from the centers of galaxies.
Supermassive black holes, right. Millions or billions of times the mass of our sun.
Yes. We see stars orbiting the centers of galaxies, like our own Milky Way, at incredible speeds around something invisible but extremely massive.
Like in Galaxy M87, the one they actually managed to sort of photograph.
Exactly. The Event Horizon Telescope image of M87's shadow is powerful confirmation. It matches the predictions for a supermassive black hole perfectly.
And these giants could power things like quasars, those super bright objects far away.
That's the leading theory. Quasars are thought to be powered by enormous amounts of gas and dust falling into supermassive black holes at the centers of young galaxies.
All that spiraling, heated material releasing incredible amounts of energy.
Immense energy. And sometimes, this process launches powerful jets of particles out from the poles of the black hole at nearly the speed of light. We see these jets stretching across vast distances.
Amazing. Cosmic engines. The book also floated the idea of primordial black holes. Tiny ones.
Ah, yes. A fascinating possibility. These wouldn't have formed from stars collapsing now.
Because they'd be too small, below that Chandrasekhar limit.
Right. The idea is they might have formed in the chaotic, incredibly dense conditions of the very early universe. Tiny fluctuations in density could have collapsed directly into black holes.
So, leftovers from the Big Bang itself, have we found any?
Not definitively. It's a hypothetical population, but people are looking for subtle signs they might exist. Tiny black holes from the dawn of time.
Okay, so the evidence seems pretty solid, from stellar mass ones to supermassive ones, maybe even these primordial ones. Which brings us to Chapter 7, and the title is just fantastic. Black holes ain't so black.
It really grabs you, doesn't it? Because it seems like a total contradiction.
We just spent all this time establishing they trap everything. How can they not be black?
Well, this is where quantum mechanics enters the picture in a really unexpected way. It started with Jacob Bekenstein.
What was his idea?
He was thinking about entropy, the measure of disorder in a system.
The second law of thermodynamics, entropy always increases. Things tend towards disorder.
Exactly. Bekenstein noticed something odd. When matter falls into a black hole, its entropy seems to just vanish from the universe. That looked like it might violate the second law.
Uh-oh. You can't violate the second law.
Physics police will get you. So Bekenstein suggested maybe the black hole itself has entropy, and maybe that entropy is proportional to the surface area of its event horizon.
So as stuff falls in, adding entropy, the black hole's area increases and its own entropy goes up, keeping the total entropy happy.
That was the core idea, an incredibly bold suggestion at the time.
But wait, if something has entropy, doesn't that usually mean it also has a temperature?
That's the crucial link. In physics, entropy and temperature are deeply connected. If Bekenstein was right, and black holes have entropy related to their area, then they must also have a temperature.
And anything with a temperature radiates energy, right? Like a hot poker glows red.
Precisely. Any object hotter than absolute zero radiates. So this implied black holes should radiate, but how? Nothing's supposed to get out.
It sounds like a paradox. Did people believe Bekenstein?
There was a lot of skepticism initially, myself included, actually. It seemed to fly in the face of what a black hole was.
So what changed?
Well, things started shifting during a visit to Moscow. I had discussions with Yakov Zoldovich and Alexander Starobinski.
Two other giants in the field.
Absolutely. And they argued, quite convincingly, that rotating black holes should create and emit particles due to quantum effects near the event horizon linked to the uncertainty principle again.
Quantum mechanics muddying the waters or lighting things up.
Huh? Depends on your perspective. Their arguments spurred me to do the calculations properly, using quantum field theory in the curved space-time around a black hole.
What were you expecting to find?
Honestly, I was trying to prove Bekenstein wrong, or at least refine the rotating black hole emission idea. I thought non-rotating ones would still be perfectly black.
Well,
But the math didn't agree. To my initial annoyance, actually, the calculations showed that all black holes, rotating or not, should steadily emit particles.
wow. So you discovered what we now call Hawking radiation almost by accident, trying to disprove the initial idea.
Something like that. It was quite a surprise. It meant black holes weren't truly black after all. They have a faint glow.
Okay, but how? If nothing escapes from inside the event horizon, where does this radiation come from?
That is the absolute key. It doesn't come from inside. It originates in the seemingly empty space just outside the event horizon.
Empty space isn't really empty in quantum mechanics, is it?
Exactly right. It's fizzing with activity. Quantum fluctuations constantly produce pairs of virtual particles, a particle and its antiparticle.
Like borrowing energy from the universe for a split second.
Sort of, they pop into existence and normally annihilate each other almost instantly, repaying the energy debt. Very fleeting.
Okay, so these pairs are popping up everywhere, including near the black hole's edge. What happens there?
The intense gravity near the event horizon can do something weird. Imagine a virtual pair appears right at the edge. One particle might have positive energy, the other negative energy.
Relative to someone far away, you mean?
Yes. Now, normally the negative energy one is forbidden. It can't exist for long as a real particle out here. But near the black hole, it's possible for that negative energy particle to fall into the black hole.
It crosses the event horizon.
It falls in. And once inside, it can exist as a real particle with negative energy. It effectively reduces the black hole's total energy.
Okay, so the black hole swallows the negative energy particle. What about its positive energy partner?
It's now left alone. Outside the event horizon, its partner is gone, so it doesn't need to annihilate anymore. It's been, well, promoted to a real particle.
And it can't escape.
It can escape. It flies off into space.
Yeah,
To a distant observer, it looks like the black hole just emitted a particle.
that is incredibly clever. So
Yeah.
the black hole isn't leaking stuff from inside. Its gravity is sort of catalyzing particle creation just outside its boundary.
That's a great summary. The black hole's presence allows this quantum process to happen, resulting in radiation escaping.
And since the particle falling in had negative energy,
It reduces the black hole's total energy, and we know EMCS on.
so the black hole loses mass. Tiny amounts, presumably, but it loses mass.
Exactly. Every particle emitted carries away a tiny bit of the black hole's mass energy.
Which means over truly vast time scales, black holes can actually evaporate.
That's the startling conclusion. They slowly shrink as they radiate.
Is the radiation rate the same for all black holes?
No, and this is crucial. The temperature, and thus the radiation rate, is inversely proportional to the black hole's mass.
Meaning smaller black holes are hotter.
Much hotter, and they radiate much, much faster. A black hole with the mass of the sun has a temperature incredibly close to absolute zero. Its evaporation rate is minuscule,
It would take longer than the age of the universe to disappear.
far, far longer. But a hypothetical black hole with the mass of, say, a mountain would be incredibly hot and radiate away its mass very quickly.
And those primordial black holes, if they exist and were small enough,
They could be evaporating right now. If one formed with a low enough mass early on, it might be reaching the end of its life today.
how would that end look?
As it gets smaller and smaller, it gets hotter and hotter, radiating more and more violently. The very final stage would likely be a massive burst of energy, probably high-energy gamma rays.
Are people looking for those bursts?
Oh, yes. Searches for unexplained gamma ray bursts that could be the signature of evaporating primordial black holes are ongoing. No confirmed detections yet, but it's an active area.
And this whole process, the black hole losing mass and shrinking, its entropy would decrease too, wouldn't it?
Yeah.
Does that mess up Bekenstein's original idea about the second law?
Good point. But no, it works out beautifully. The entropy of the emitted Hawking radiation is actually greater than the entropy the black hole loses by shrinking.
So the total entropy of the universe, the black hole plus the radiation, still goes up. The second law is safe.
The second law remains inviolate. It's a wonderfully consistent picture.
It really is. So wrapping this part up, We started with black holes forming from collapsed stars, defined by this inescapable event horizon hiding a singularity.
Absolute prisons of gravity.
But then, quantum mechanics throws this amazing curveball: Hawking radiation. The idea that pairs of particles popping into existence near the edge can lead to the black hole emitting energy.
And therefore losing mass, shrinking, and eventually possibly evaporating completely.
It's just, wow, that realization that even these ultimate objects aren't necessarily forever, that they obey quantum rules too, that's a definite aha moment.
It truly bridges the gap between general relativity, the theory of gravity and large scales, and quantum mechanics, the theory of the very small. It hints at a deeper, unified theory we're still searching for.
It really makes you think, doesn't it? If these ultimate cosmic prisons, black holes, can fade away, what does that imply about permanence anywhere in the universe?
Exactly. And think about this. If empty space isn't really empty, but the sea of virtual particles being influenced by gravity, what else might be going on in the vacuum that we haven't even dreamed of yet?
Deep questions indeed, plenty to ponder there, and a perfect place to pause our exploration for today.
A fascinating journey through some truly strange territory.
Absolutely. Thanks for guiding us through it. Join us next time on The Deep Dive as we continue our voyage through the biggest ideas in the cosmos.